Okay, once again, hello everyone. I will continue now my second part of the two-day lecture. We have seen that the time-dependent acceleration for curved path, that is, we have the tangential component which time-dependent. If we integrate now this acceleration, the tangential one, we have the velocity, which is the integral of the tangential part, and plus constant integration constant, C1. And if we come to the position that we have double integral of the acceleration, then we have the second constant, C2. Then we have here the velocity at time t equal to 0, we have V0. Then we get C1, the constant C1 is equal to V0. And for the position at time t equal to 0, we have S0 initial position, and we get C2. That is mean if we are on place now, we get the expression for the velocity and the position. We take the case of distance-dependent acceleration for curved path. Then it means that here we have AT, which is it depends on the position or the path. And here, if we are replacing the previous equation, then we get the following expression here, which is the half of V square, depending on time, minus V initial velocity square, and the integration from the position S0 to ST of the tangential acceleration, with respect to the new position. We have the third case, which is the velocity-dependent acceleration for curved path. That means instead of the position, now we have the velocity for the tangential component of the acceleration. Then we use also the previous case or the previous expression in the slide before. Then we have here ST, which is time-dependent minus initial position. We integrate with respect to the velocity here, and we get the time t. It's from V0 to Vt, the active initial velocity, to actual velocity, dv over dt, which velocity dependent. We take the example of circular motion. That is means in this case, the vector r, it's in our case here, is constant. It's the radius of the circle. And we have the motion, which is the particle motion here at time t and t plus dt, covering here now the distance ds, small distance with small angle d phi, and we have for the coordinate system xy, we have here the angle phi. That is means that we have only circular motion. The particle at each time here will be described by the angle phi and the constant radius r. Then we have the path velocity v, it's ds over dt. That is means time derivation of the position, and we can get thus ds. It's only here ds is only r d phi. That is means if we get the we take the tangent of the small angle d phi that we have here, tangent d phi, it's only ds. multiplied by r, divided by r. Then it means now here the tangent d phi will be equal to d phi as it's small angle. That it means that we have sinus d phi it's d phi, and cosinus d phi it's near to 0. In this case it's 1. Then we can make that the tangent d phi is only d phi. Then we get here ds is r d phi. If we replace in this equation here for the velocity, then we get v, it's r, the radius d phi over dt, and here this d phi over dt, we call it the angular velocity omega. Omega is only phi dot. Then we can write that v is only r multiplied by omega, and it's equal to r phi dot. The unit of this angular velocity omega is only 1 rotation per second. That it means if we make the whole circle rotate with 360 degrees in radial description 2 pi, then we get here omega is 2 pi divided by 1 radial divided by second. The tangential acceleration in this case can be described by at, it's dv over dt, and it's r omega dot, and omega dot, it's only phi dot dot. This phi dot dot will be called the angular acceleration. That it means omega dot is only phi dot dot, and omega it's phi. Then we get here the normal acceleration. It's only the velocity square divided by r, with v, it's r omega. Then we get the normal acceleration. It's r omega square, and it's r phi dot square. En is always directed toward the center of the circle. That it means now if we look to the then we have here at this point, for example, at t plus dt, we have the tangential at of the acceleration, and we have the normal one, which is perpendicular to at, and this is the component, the normal component of the acceleration, and here it's directed toward the center of the circle. Now, if we have uniform circular motion, that it means we have phi dot dot the acceleration, or the angular acceleration is equal to 0, then twice integration over the time. Then we get phi dot, it's constant c1, and phi it's c1 multiplied by t plus second constant. If we take always, when we make the integration, we have two constants, or we are dealing with the velocity and the position in either in radial or in circular case. Then in this case that we have to define two constants of integration, C1, C2, and this can be defined by the initial conditions. In general, we know the initial conditions. Then in our case here, we take t at time t equal to 0. Yeah. At rest, there is phi 0, and phi dot, which is the angular velocity, it's equal to omega 0. Then we can get the constant C1 and C2. Then we inject them in the equation. Then we get phi dot, it's only omega 0, and phi is omega 0 time t plus phi 0. If we take now the case of uniform accelerated circular motion, that it means that we have phi dot dot, it's equal to constant. In this case, that phi dot, which is the angular velocity, is linear with the time plus C1, and phi is quadratic with the time, and we take here the second constant of integration. The same way, for the initial condition, we have phi 0 and omega 0 at time t equal to 0, then we get C2 and C1. We replace them in this equation, then we get the angular velocity, which is linear with time, and the curvature, or let's say the position, it's phi, it's quadratic with time. Then we take the case of the description of motion in polar and cylindrical coordinate system, while in this case that we have sometimes very difficult to describe the motion in Cartesian coordinate system x, y, z, and what will we use in 2D? We have the polar coordinate system, and in 3D we use the cylindrical coordinate system. It's more easier to describe the motion by using these two coordinate systems, and for the plane motion we have the polar coordinates. That it means for the plane x, y, if we take this co-rotating, or that it means that we have this particle, it's rotating and let's say changing the position r. In this case, we have to take this polar coordinates, and what we do, instead to use Ex and Ey, that it means we will use the unit vector or the basis vector Er and Phi. That we look here. That it means that here, if I take this coordinate system, we have X and we have Y. Now, if we take any point here, the particle P, we will get here, instead to use the unit vector Ax and Ey, we will use this coordinate system Er and Phi. That means there is the angle phi here, and there is the vector r. This is r, which is time dependent. Then we have here outward, we have the set. That means if we look, if I rotate the system here, for example, we can represent it as follow. I can represent it as follow, that we have here y, we have x, and we have z. That is means here we have AX, we have AY, and we have AZ. These three are the basis vector or the unit vector in Cartesian coordinate system. Instead to use this coordinate system, we will use this coordinate system ER and EV. And here, of course, we have here 90 degree. Okay, that it means E phi is perpendicular to ER, and there is a vector here outward, yeah, which is HZ. Now, if I return back to the slide, then what we have here, we have, as we said, ER, and we have E phi. There is 90 degree here between ER and E phi, and there is here outward the vector HZ, or the axis Z. Then what we see here, the position of the particle at each time here, we see that the position vector R is time dependent, as well as ER is changing, as well as E phi. That is means now ER is time dependent and E phi is also time dependent. Then it means the position of P on the path through the position vector can be described now. R vector here, it's only the projection of the distance along this axis. And in this case, we projected with the unit vector ER. Then for the spatial motion, instead of the plane motion, then we use what we call cylindrical coordinate. That it means we have only to introduce this second term, which is along the direction of Z axis. Then we can say that V, the velocity, is only time derivation of the position vector. And as we said that position vector is R, ER vector, the unit vector, then ER is time dependent. Then it means we have to make time derivation of, return back here to the slide. That's what we have here. We have V, it's equal to R dot. And by definition, R is only R, E, R vector. And this is, we say, if I make like this, T over dt of RER. That it means we can write this by d over dt of RER plus d over dt of here, let's say like this, and yeah, this one, and we make d over dt. It's better to write it in another way. That's what we have here. We can write that it's d over dt of the product R ER. As ER here, it's time dependent as well as R, then we can say that it's only RT. It's T R over dt multiplied by ER plus R of dE R divided by dt. And this can be written like this, that we have R dot ER plus R ER dot, like this. Then we have here, as we said, that R dot ER plus R E dot R. In the case of cylindrical coordinate system, instead to use only in the polar coordinate system, that means in 3D case, we add these terms here, which is along the direction Z. As each Z, it's coincide with the axis Z, it doesn't change. There is only a rotation along this, or there is only a motion on the plane X and Y. There is no motion along Z direction. In this case, there is only Z dot, which time dependent, but it's Z, it's time independent. Now, if we make here time derivation of the basis vector ER and EV, that means we have this term here, E dot, the E vector R dot. In this case, we can make here the projection that we have the particle here, P, that means has the component cosinus phi and in X direction, and sine phi here in Y direction. The same we have for E phi, we have sine phi and cosine phi along Y direction. That we look here, if we see that there is the components here, vector cosinus phi, and there is the component sine phi for ER. The two are along the direction of X and Y, but for E phi, it's opposite direction to X. Then we have here, if we make the projection along now ER along X and Y direction, then we get here cosine phi for X direction plus sine phi along Y direction. And E phi, the same here, we have minus sine phi along X direction, and we have cosine phi here along Y direction. If we look now, replace here, we look to ER, what we see here, that the time derivative of ER, that we have two terms, EX, of course, and EY are fixed, that it means R doesn't change with the time. Then we have here cosine phi, the derivation of cosine phi, that there is here depend on phi, of course, and phi here what we have, it's time dependent. That it means we have phi dot, the derivative, that it means here we can say, if I return back now, we can write that here t over d phi of the cosine sine, or let's say that we have here d cosine phi divided by dt. This is equal to phi dot, that it means we can write it better. It's only d phi over dt multiplied by d cosine phi over d phi, like this. That is means d phi over dt is only phi dot, and d phi, d cosine phi over d phi, it's only minus sine phi. The same we do with sine phi. When we have d sine phi over dt, the same way we have phi dot, yeah, cosinus phi. Now, if I return back here to the slide, then we have here the time derivative, as I said, r of the vector, unit vector in radial direction. Then we make the time derivative of this terms and the time derivative of this term here. As we said, for the cosine phi, it's depend on phi, and phi depend on time. Then it means we have phi dot minus sine phi in x direction here. And for sine phi, we have phi dot cosine phi in y direction. The same principle we will be used here for e phi, yeah. And here, if we get this term here, if we make it short, let's say, this term here, you see it, it's only e phi, this one. Then we have here e phi, that is means e dot r, it's only phi dot e phi. The same principle we use for phi dot, then we get here minus phi dot er. then keep this two terms in mind. Yeah. And if we look now to the velocity, it's the time derivative of r, the vector position, the time derivation of the vector position. And in this case, what we have here, we have the radial component and circumferential, or let's say circular component. And if we use cylindrical coordinate system, we have the component in z direction. R dot will be only for r, and r phi dot will be only the velocity along the circular path or circumferential direction. In the radial velocity, for r is r dot. Circular velocity or circumferential velocity, it's only r phi dot. Circular path, for example, that here the velocity here, it's equal the orbital velocity, it's circular velocity, and the radial velocity is equal to 0. A radial motion case, special case, when we have r dot is different from 0, but phi dot is equal to 0. In this case, phi with a constant phi or phi is constant. Then we have here the second term will be equal to 0. Then we have only the velocity along the radial direction. That it means there is only translation here, yeah, and there is no rotation. Then for r, the VR, or for VR, the radial velocity is equal to time derivation of the position projected along the radial direction. Then in this case, that's what we have here, motion along straight line, like we have one-dimensional case, with phi, the angle phi is constant. Then in this case, the velocity v phi is equal to 0. Opposite now, we have the circular motion case. There is no radial motion. Then in this case, r dot is equal to 0. Then r is constant, circular path. And we have here phi dot is different from 0. The velocity will be r dot, and we take only the second term. The first term is equal to 0, yeah, considering the previous equations. That it means what we have here, we have v phi as is perpendicular to ER, and this is along the direction of the unit vector E phi, and here is r phi dot. Then if we take now motion on an elliptic path, a reference path will be here, point will be a focal point of the ellipse. Then we have here, for example, you see, we have v phi, which is r phi dot along phi direction, and we have the radial component vr, which is r dot. This is the case of the orbital problem. Then the velocity is described by v, that we have here the radial component, this one here, the velocity along the radial direction, and we have the circular component along phi direction. And in case if we introduce the cylindrical coordinate system, and we take the case of the third component along z direction, then we have here z dot hz. that we looked at here, V phi is respectively only the tangential, respectively different from the tangential direction. You see here, V phi is different from Vt, as here it's, if we take in this direction, that we see V phi is in this direction, but it's not the tangential component. We see here that V phi, if it's this point rotate, V phi here, it's only equal to the tangential component as it's tangent to the elliptic path. Now, if we take the velocity, it's r dot, then we have here the radial component, circumferential component. This is the expression that we got previously. And we get now the acceleration. The acceleration is only twice derivation of the position vector. That we see r dot, we have to make the derivation of this term. It's composed of two terms, and each term is time dependent. The same here, you have V phi, V phi. In this case, what we have three terms. That it means each term R, phi dot, and E phi are time dependent. Then we get the first one, it's dr dot over dt multiplied by er. This is, we get this term here. And then we make der over dt multiplied by r dot. Then we get the second term here. For this term here, along phi direction, we have r dot dr over dt, which give r dot multiplied by phi dot e phi. And then d phi dot over dt multiplied by r e phi. This is the term. And the third one is d e phi divided by dt multiplied by r phi dot. That if we assemble whole terms along radial direction and phi direction, then we have two terms here along r direction, but there is the point where e dot r, it's only phi dot e phi, as we have seen two slides, we have seen 2 or 3 slides before. The same for phi dot here, it's only minus phi dot er. Then we assemble the terms in the radial direction, er, we have 2 terms here and 3 terms here. This is the r dot phi dot, we have r dot phi dot here, e phi, then 2 times r dot phi dot in the direction e phi, and plus r phi dot dot e phi here. And for the same for radial direction, we have r dot dot, and here minus r phi dot square. Now, if we look here in a polar coordinate system, what we have 2 components of the acceleration. The first one is the radial one, and the second one is the circular one. Now, we can write the acceleration vector. We have ER, which is the radial component, if phi, which is the circular one or circumferential one. Each term ER and E phi are given by the following equations. In the case of a radial motion case, that means phi dot dot is equal to 0. Then phi dot is equal to 0. That means phi is constant. Then in this case, we have the acceleration, which is given by the following expression, or it's where r dot dot is given by phi dot r. This is the time derivation of the radial velocity. Then in this case, there is only a radial acceleration. That means there is only on this direction. Then this is, we can call it that the velocity relative. That means there is only motion along this direction here, yeah, as phi dot dot are equal to 0. In the case of the circular path case, that means r dot radial component, the velocity and the acceleration is equal to 0. Then we have r, which is constant, yeah, as its circular path, and we have phi dot and phi dot dot are different from 0. The acceleration E, it's only r dot dot, and we have replacing the previous equation that we get the following term for the acceleration. As you can see here, for the acceleration, there is two terms. Beside that, there is only circular path case, but the acceleration has component in phi direction, circumferential direction, and there is component along the radial direction. As you see here, this term is with minus, that it means is inward to the center of the circle. Then we can say that there is two components. This one, which is tangential, and this is, which is radial or normal to the circumferential or the tangential one. Then in general case that we have here, r dot different from 0, phi dot different from 0, and r dot dot and phi dot dot are arbitrary. In this case, we have the acceleration given by this, as we have seen it before, by these two terms. We have ER and EV, and this term here is called Coriolis acceleration and will be noted by EC. In case of two-dimensional case, that we have 2 times r dot v dot EV, and in general case, three-dimensional case is only the vectorial product of 2 times the angular vector of the angular velocity and the relative velocity. Then it means we have here, we look that here, A Coriolis is 2 times r dot phi dot, and it's along phi direction. Phi relative is only r dot, and this is along a radial direction. And here we have the angular velocity omega, it's only phi dot, and omega is outward, yeah, on this plane ER and EV. Then we have here omega, it's given by the following expression, phi dot along z direction, as it's perpendicular to the plane ER and EV. And we have here relative, it's given always in the radial direction, it's the translation. Then we see the relative motion of the considered point P with the velocity r dot in the radial direction on a rotating frame system with angular velocity phi dot. The tangential velocity is considerably basing horizon that we have here vt in the radial direction. Yeah, this is the tangential one, and we have only here the translation. As you can see, this is the component of t, and here it's equal to 0 as its fixed point, and you have the motion in time t and t plus dt. Then it's required for this acceleration, yeah, the Coriolis term. That if we take the special case of motion, when we have here acceleration is always directed to one point, and the center set here will be elliptic focus, for example, planetary motion. Then we have the time t1, t2, t3, t4. And if we take here now this part at time t and t plus dt, then we have here this, let's say, the new position or the distance between the time of the particle at time t plus dt and t is only rt t phi. The vector, the angle here d phi, it's small. Then we can say tangent d phi, it's only d phi, and we can describe here by rt multiplied by d phi. Then the planet is held by gravity in its orbit, of course, and there is the acceleration, circular acceleration, E5, yeah, is only r phi dot plus 2 times r dot phi dot, and this is it's equal to 0. There is the intermediate calculation. For example, here, if we see d over dt of r squared phi dot, r it's time dependent, phi dot also time dependent, that we have here 2 times r multiplied by r dot phi dot plus r squared d over dt of phi dot, and we have here phi dot dot. Then if we can simplify the expression here, we get the following, and if Ein's 1 over r d over dt of r dot phi dot is equal to 0, then we get here phi dot is inversely proportional to r squared. Then it means when the planet approaches the sun, its angular velocity increases. Okay, I have finished with the lecture. I would like to thank you for your attention and hope that now it's more clear. If you have questions, or you can go to Mrs. Lea, or you send me an email, or you can ask in the next lecture or next tutorial. Thank you and bye.